All right. Still a few people trickling in. I'm going to give it another 30 seconds and then we will kick off. Appreciate everybody joining early. It's great to see you all. Hopefully a interesting session. I'm excited to see some of the questions and talk with you all. So super stoked. I think we can kick off. Anybody else trickles in, I'm sure they'll catch up. So first off, I want to say hi. My name is David Hershey. I'm a solutions architect at Tecton. I've been working with our customers in a whole bunch of verticals for a long time, fraud being primary among them. So excited to just chat with you about the platform. A few things to know about the session. I know everybody is muted, and so if you have any questions, please shoot them to me in chat. I'll have the chat open the whole time. I'm happy to either answer throughout as possible, and there will also be time for questions at the end. So if you want to stage them up or just save some questions towards the end too, there should be plenty of time to ask questions, and I'll be on for the whole hour helping to answer anything and any curiosities people have. With that said, the primary topic today, thank you all for joining, and we're going to be talking about fraud detection, and in particular, some of the data challenges in fraud detection. So these are things I've seen over and over again working with our customers that are building out risk models. And so we'll touch on really two primary things throughout the chat today. It's going to be first, low latency stream aggregations. We'll talk a little bit more about those, and then also just how you handle very real-time data. And big things that we want to talk about is then how specifically Tecton solves those. So this will be really focusing in on how Tecton can empower your team to very easily and quickly build these types of features that end up being really critical for fraud detection models. So with that said, let's dive into each one of these problems in a bit more detail. Then we'll set an actual problem statement, and we'll go into a bit of a hands-on demonstration of how you actually build some of the stuff in Tecton. So first I want to talk about low latency aggregations. An example of the type of feature that people talk about here is something like the number of transactions that some user has made in the last 30 minutes. Why does this matter? Fraudsters just take advantage of timing ruthlessly. If they find out that you update data daily, they will do things on a smaller time domain. And essentially, you just need as much information as quickly as possible. So knowing someone made 10 transactions in the last minute is going to be super crucial to catching some forms of fraud. And the reason I want to talk about this isn't just because it's important, but also because it's traditionally one of the more challenging features to implement. So when you think about doing this, it's pretty trivial to do offline frequently. If you just have historical data in a warehouse, you can write your 10-minute aggregation, 30-minute aggregation, all you want. SQL's great. The thing that really blows up is then when you want to get that data available in real time, and there really just isn't very simple, very efficient tooling to build these types of aggregations in the real-time setting. Obviously, you can process streaming data with Spark Streaming or Flink or something of the like. But even within that, there's a lot of ways, like if you just write a group by on some Spark SQL in Spark Structured Streaming, there's a lot of ways that that can explode from an infrastructure perspective, and the cost of constantly just processing that stream can get really expensive. So we'll dive into a little bit about how Tecton actually handles low latency stream aggregations, how we can do it efficiently, and some of the performance benefits you can get by doing that. And then the second type of feature I want to talk about is what I'll call real-time features. There's a lot of real-time data, so I want to talk about exactly what I mean. But basically, if you have data right now, the user just made the transaction, You can't wait to send that to a stream, wait for it to be processed, calculate features. You need to calculate features about that transaction right now. Something like, is the amount of this transaction greater than the average amount of a transaction that a user has made? Again, why does this matter? If you can't build features on top of the like what's happening right now, what are you really doing at all? And the challenge here actually ends up typically being online-offline parity. So if your data scientists build some features from their data warehouse about historical transactions they have, re-implementing those exact features that they built online can be relatively challenging. Typically, you need to like actually re-engineer the implementation to make it efficient. A lot of times it's not simple to just integrate arbitrary Python in with your production system, especially not in a performant way. What we're going to talk about to address that is a feature that Tecton has called on-demand features, which allow you to process request time data right at request time, turned into features, and then also run that feature transformation logic both at request time when you're making predictions, but also when you're generating training data. I'll show you a little bit about how that works. So how this is all going to come together for the demonstration today is essentially we can imagine a service where users are making transactions from their phones. And I just want to step through sort of the data model for the simplified stuff we're going to walk through today and how things are going to happen. So you can imagine user makes a transaction and that's going to produce some, talk to some transaction backend. And it's going to produce, first and foremost, some sort of event that contains data about that transaction. So we're going to stream that in this case to a Kinesis stream, and that will sort of buffer those events that are happening. But then as soon as they make the transaction, essentially what we're going to do is call some sort of fraud service that we have. So we're going to pass information about that transaction to this fraud service. That fraud service is going to, the goal is essentially to call some ML model. You can imagine something, say, deployed in SageMaker to get back a prediction of whether or not the transaction is fraudulent and send a decision back to the user. And in this case, what this service is going to do is going to call out to Tecton to retrieve features, actually. Now, how is Tecton going to compute those features? They're going to come from a few places. The first is Tecton is going to listen to that Kinesis stream I told you about that is buffering those events. So from this stream, it's going to do things like those low latency aggregations I told you about and just get sort of real-time information about transactions as they're happening. That stream is also writing data to a data lake. And so any like long duration historical features like lifetime aggregations or things like that, Tecton is going to actually be computing features from the data lake and pre-computing them and making them available. And then the last source of features that we'll touch on is features that will be computed at request time. So transaction will come from the phone to the backend. That information about that transaction will be passed to the fraud service. And then the fraud service is going to send information about that transaction directly to Tecton when it asks for features. And some featureization is actually going to happen within Tecton here. And so just to recap, people are making transactions and we're thinking about data from really three places: request time, streaming, and from our data lake for longer historical data. And we'll step through in the course of the next half hour or so how we're going to build sort of all of these different types of features, what this data actually looks like, and we'll piece it all together to show you what it actually looks like to then, say, generate training data down the road. So without further ado, I'm going to jump into a notebook where I just want to get started exploring some of this data, understanding a little bit more about the system and actually implementing some of these things in Tecton itself. So the first thing I want to talk about is this raw data. And to do that, I just want to basically tap into this Kinesis stream and listen to actually looks like. So this is going to be simplified for the case of this demo, but essentially what I want to do is just start a preview of a streaming data source. So basically, we're going to use Tecton to grab a data source that we've registered with Tecton. So we basically already told Tecton about this Kinesis stream. And I'm going to use this initiative or this function here that Tecton has to basically start a preview of that stream. What that will let us do is actually start to preview this data live as it's coming in. So what this data actually looks like, really simple, but basically someone is sending money to someone else, and this is the amount of the transaction. We don't know anything about fraud yet because it's not there, but we do have information about basically like what types of transaction is happening, the timestamp at which that's happening. And over time, we should expect more and more data to come in. So you can see we've seen 32 rows since I started listening here. So this is what we're working with. We have this raw data in Tecton, or raw data in this Kinesis stream. Tecton is aware of it, but now from here, what we want to do is actually go build some features. I see a hand raised in the chat. By all means, please shoot a question in the chat, and I am happy to respond there. So one of the questions I have here is, in the architecture, transaction events accumulated into features in parallel of user requests to get features may lead to stale feature values. Is there a way with Tecton platform to monitor such events occur, to identify places where on-demand features can be used? Yeah, we'll get into this a little bit, but there's a lot of monitoring in Tecton to sort of tell you the freshness of features, how long it's taking from events happening to features being calculated. I can probably show you an example of this in the UI in a second, and we'll get into a little bit of the monitoring and information you can unpack in Tecton about these features as they're being calculated. I'll show you that in a moment, actually. And I'm happy to make this notebook available after the demo too. We can send that out. Okay, so the first thing I want to do, I'm going to table a question for a second and move forward, and we'll get back and answer a few more in a second. So the first thing I want to do is basically define some baseline features that basically aggregate historical metrics about the transactions that an individual user is making. And before I even show you how we do that, I basically just want to show you what these features look like. I've already built them in Tecton. We'll get into how they were built, what they look like. We'll show them in the Tecton UI too. But the feature that I've built is this thing called user transaction amount metrics. And it contains metrics about historical transactions that users have made across various time windows. So for example, this is saying this user, as of September 8th, the average amount of a transaction that they had made in the last hour of that point is this much. It looks like that's the only transaction they've made for a while. So that is the total. And most of these people, looks like, have only made one transaction across this 3-day time window. But we're basically just getting metrics about the average size of a transaction a user has made in some time window and the total amount they've spent in some time window. So what I want to do from here is actually unpack this feature. I'm going to show you a little bit about how we can view, like how this feature came to be, how we can see it. I'm actually going to show you the definition of it. And then from there, we're going to go in and build those two new kinds of features I told you about, the real-time transaction counts that are really low latency, and that on-demand feature I told you about, whether or not a user has a transaction or the transaction is higher than the average transaction. And before I do that, I'll pause and answer this last question in the chat. In the architecture diagram, the source for streaming was shown as Kinesis. Is there a possibility of it being a TCP stream? Right now, the only streaming support that Tecton has is for Kinesis and Kafka. So we can plug it into a Kinesis stream or a Kafka topic and listen to that to consume data. Those are the two ways that we can consume streaming data. All right, let's head over to Tecton's UI, and we're going to start looking at this feature, these metrics about historical transactions users made. First thing I see when I pull up a UI, the UI is just a dashboard of everything that exists in Tecton. And so if I want to actually go inspect an individual feature, I'm going to head to this features tab. This is going to provide me a list of all of the features that I have access to. And the one that we were just looking at is user transaction amount metrics. So this feature is just what I said, transaction amount statistics across various time windows. The main thing I want to show you is the pipeline that is actually running here. So the first thing to know about Tecton is Tecton really handles the whole end-to-end of the computation of features. So Tecton plugs all the way into raw data sources, processes data, like is in charge of either consuming directly from a stream or running jobs against batch data sources to update features. It calculates features and then it handles storing them such that those features can be consumed by your ML models. So in the case of this feature that I was showing you before that contains metrics about historical transactions that a user has made, the data is coming from a Kinesis stream, the one I showed you that contains that data about transactions. We saw that preview just a second ago. That data is going through a series of transformations to compute those different time window aggregations that we saw. And it's being persisted into two different storage layers that Tecton is managing. One is what we call online. This is where you can imagine the latest value of all these features is stored so that in real time, I can look up transaction metrics about a user. The other is what we call our offline feature store. This is where we're going to keep track of historical features through all of time, and we'll use this to generate training data for our models. And so a lot of what you're doing in Tecton and what we did to make this data that we were looking at available was essentially to implement this data pipeline in Tecton such that everything is being calculated. I'm going to answer a few questions here. So first off, this data flow diagram is automatically generated. The nice thing about Tecton managing the end-to-end is it really can capture the whole metadata of everything from raw data to features, even to the consumption of those features by downstream processes. So Tecton becomes a pretty comprehensive platform for tracking and understanding the metadata associated with these feature pipelines. A couple other questions in the chat. You are essentially defining features here. So Tecton isn't building features for you for the most part. We're really taking, and what Tecton's quite good at is taking this transformation logic that you're defining, whether that's PySpark or SQL or whatever it may be, and then helping you turn that into a data pipeline that makes that data available. And last piece is can we consume Kafka across clouds? So a few things to know. Today, Tecton is only available on AWS. We can consume Kafka from whatever broker is there. That's easy to do. But right now, the Tecton itself only sits in AWS. All right. So now we've seen this pipeline. And the last thing I want to show you is how do you actually how did this pipeline come to be? How did we define this data pipeline in Tecton such that these aggregations were being calculated from this stream and being stored? And where that happens in Tecton is actually in this declarative code API. A lot of information here, but I'll step through it a little bit slowly. We'll comment out to look at what we're looking at. When you build features in Tecton, you declare them as code. What that means is if your team is using Tecton, your team is essentially collaborating on a Git repository that defines or that contains all of the definitions of all of the features that you want to build. So if you want to go build a new feature in Tecton, what you do is essentially open up that code repository and write some code that defines a feature. In this case, we're going to build this stream aggregation. And for stream aggregations, we have a special type of feature. So the transformation logic, all it needs to do is essentially surface individual events that we want to aggregate. So what this transformation logic does is basically from that stream that we looked at, it selects the user ID, the amount of the transaction, and the timestamp of the transaction. And then we're actually going to use Tecton to do the aggregation logic. So we were looking at doing the average transaction a user has made in some time window and the total amount they've spent in some time window. The tool that you have in Tecton to do this is what we call our stream window aggregate feature view. So to turn this transformation logic into a feature pipeline, essentially you just add this decorator that Tecton provides that helps you turn it into one of those pipelines. And this stream window aggregate feature view that Tecton provides is the primary tool we have to make it really, really easy to define transformations against streams. Once we get into the really low latency aggregations, I'll talk a little bit more about the mechanics of how these aggregations work. But for now, the main thing I want to focus on is to define the actual aggregations. You essentially just include this argument here that defines the column you want to aggregate, the function you want to use to do the aggregation, and the various time windows that you want to aggregate across. And so what this is doing is what we saw before. It says aggregate the amount of the transaction, the average across various time windows, and turn that into features. Some other key components of this that are going to be relevant as we move forward. One is this thing called the aggregation slide period. This is going to define how often we want to update these values online. So here, by saying 10 minutes, that means new values of these features will be calculated and and returned from the online store every 10 minutes. And so as transactions come in this case, these tickers aren't sort of continuously updating. They're updating every 10 minutes to take into account the last 10 minutes worth of data. We'll talk about how we can drive this down to really low time periods when we build the transaction counts in a minute. Another thing to note is this schedule. So when you build streaming features in Tecton, we also plug into a historical record of the stream, something like your data lake or data warehouse that contains historical transactions from the stream in this case. And then we can use that to calculate all of our historical data. So what we do is essentially run batch jobs at some schedule that fill in historical data in the offline store. And we'll use that for generating training data. So what that means is if you define a feature in a month, you still get to use data from the last month when you're training your model, and Tecton can automatically compute features historically. Anyway, all of this comes together to be the code that's necessary to build that pipeline that I showed you before. So again, what we're really trying to do is make it really simple to define some transformation logic and some aggregations, and to have that explode into the orchestrated and managed data pipeline that's actually computing these things and doing it efficiently in the case of the stream such that things don't explode. I'll answer a couple of questions that have popped up now. First off, do we have access to the offline feature store to build new models from the features in the offline feature store? And yeah, you do. And I'll show you what some of those APIs look like in a minute of how you actually query this data out once that data is being computed. Next is how do you deal with time frame overlaps? In this case, as we're processing these streams, we essentially calculate tiles of data. So what I mean by that is as this data is coming in on the stream, we're reading chunks of data at a time, writing out tiles of aggregations to our online store. A lot of complexity, technical complexity there, but essentially we're intelligently writing and efficiently writing some pieces of the aggregation. And then when you request the feature, we roll those up efficiently into the feature value. And the last question is how do you handle the backfill? And the short version of this is when you define a feature, Tecton basically will kick off a series of jobs that are responsible for calculating segments of the historical feature data. So here we asked for a backfill back to July 1st of this year. That's what this feature start time does. And so when we defined this feature, Tecton will actually have created a bunch of Spark jobs in this case that are going to take chunks of the raw data, compute these features using the same logic we use online, and persist the features to the offline feature store. And that's because Tecton's aware of things like the timestamps column and the partitions in the underlying raw data. Okay, I'm going to head back now to the notebook where we were looking at things. And I want to get on to the two sort of main events for this webinar, that really low latency streaming use case and the real time. And we'll get started with the low latency streaming use case. And in this, I just want to explode out a little bit more how Tecton actually does these efficient stream aggregations. So you can imagine when you're working with a streaming source, events are coming in all the time. So people are making transactions in this case, they're happening all the time. What Tecton actually does is process that stream into these things we call tiles. What that means is we process some data at a time and pre-compute the aggregation in certain tiles of data. So for example, if we're counting how many transactions users had in the last 30 minutes, then what we'll do is say every 10 minutes, we'll calculate how many transactions do they make in that 10-minute period. Then when you request feature data, we essentially go look up the values from those various 10-minute periods. We sum them together to compute the total number of transactions the user has made in the last 30 minutes. And we spit that back out to your, as a single feature, the total number of features or of transactions the user has made in 30 minutes that you can pass into your model. The upshot of this is instead of trying to process every time 30 minutes of data from the stream, we can efficiently compute these tiles and then do a really efficient roll up of this data at request time. And then we can also do some intelligent things like compacting this data over time to make sure it's as efficient as possible to look it up. So let's actually head over now and look at what it would take to implement this real-time transaction count for a user in Tecton. I'm going to head back to that code repository we were looking at before, and we'll pull up the definition I have for this. So the first thing to know, this is going to look just like those metrics from before. So I'm going to use that stream window aggregate feature view again, which means all I need to do is expose the events that I want to aggregate. In this case, the query is going to expose the user ID, a simple one to indicate that there was a transaction that happened from that user. And again, the timestamp. And then the main difference that you'll see in the definition of the feature view in this decorator, the first is the aggregation. I'm going to do a count, and we're going to do it across 3 time windows in this case, a 1-minute count, a 5-minute count, and a 30-minute count. So this means the features that I'll expect here is how many transactions has the user made in the last minute, how many have they made in the last 5 minutes, and how many have they made in the last 30 minutes. The other big piece is this aggregation slide period is now written as continuous. So remember before it was 10 minutes. That meant that every 10 minutes, we basically have a new value of the feature available online. What continuous means is as soon as an event is processed, we're going to update the aggregation. What this buys us is essentially as fast as our streaming infrastructure is how fast Tecton will be able to pull and update feature values. In practice, today what we'll see is this will probably be about a second between when an event happens and when these features are updated in Tecton. There's even more aggressive performance optimization you can do behind the scenes depending on the streaming infrastructure itself to make it so that Tecton can pull as quickly as possible to get new events and update these features. So we've defined this feature, and again, I'm going to pull this open in the UI. So I have this continuous transaction count here. And the pipeline, very similar, coming from the stream, doing these aggregations, calculating these really small window aggregations and persisting them to the feature store. I want to call out here, I've also defined a second one of these that has longer window trend or longer window aggregations. So for example, 1 hour, 24 hours, 72 hours, and 30 days. And what I did, and the reason that I did this separately, is when you use this continuous streaming, you're essentially trading off how much compute processing and storage is used versus how fresh you need to know data. In the case of a 1 minute aggregation, I want to know that in real time. So I want to use this continuous processing. But for something like this 1 hour or longer aggregations, maybe I'm okay with that only updating every 30 minutes because the noise, it won't be as quick. So either way works. Let's look at what it actually looks like in the data though. Let's use this feature, see what it looks like and test the performance of it a little bit. So the first thing I'm going to do is grab this feature from Tecton. So I'm going to use the Tecton SDK to get this feature view called the user continuous transaction count. And the first thing I want to show you is some historical data from last week that I grabbed earlier. So I used our get features method and I asked for features between now and 7 days ago. And you can see what came back is this user, as of this point in time, they made 1 transaction basically at that point in time, which means all of these aggregations were 1. This isn't very exciting because most people only make 1 transaction in the window. And so to spice it up a little bit, let's actually just send some events to a stream and we'll pull this in real time. And it's just like give you a view of what this actually looks like to interact with this data as features are coming in real time. So in these cells, essentially what I've done, I have, this one is basically going to generate a random event and shoot it off to Kinesis for this test customer. And then this cell is going to get a feature vector from Tecton. Now, I'm going to run this first. And the first thing we'll see is there are no transactions in any of these time windows right now. So the 1 minute count is none. The 5 minute count, none. 30 minute count is none. But I want to call out this method right here, get feature vector. This is actually going to the online feature store. So what that means is this is going to our real-time endpoints at Tecton. It's going to query into the online feature store. And so we're getting the value right now when we query with this. So let's start. Let's send an event here. That sends an event off to Tecton. And now query again. And hasn't updated yet. Looks like the stream is a little behind, but we'll keep pulling this and should expect this to trigger momentarily. I wonder if the stream is down. Hopefully not. It does look like the stream processing is potentially a little behind. Our cluster went down. Classic at demo time, the cluster goes down. It's fairly uncommon. It will catch up as soon as it is back up. So I expect this to come up, but probably under provision right now. Oh, there it is, of course. All right. Well, the real-time thing clearly had to have a hiccup while I was here, but you can see I sort of hit that one and then did this, and that was a real quick update that time. We'll continue to send events and monitor how quickly this update happens, but these will update through time. So we can see this third one came in. The first one has already cycled out. So now our count from the last 30 minutes is 3, but our count from the last 1 minute is 2. And this is essentially, in real time going to update as we send events here and handle these aggregations. So there's that fourth event that we just sent. And all of these are updated. So here you can see basically like in real time, these aggregates are responding, and you can imagine, now you've got your model, you can consume these signals in very real time and handle these aggregations very quickly and efficiently. And the other thing to note is because of this tiling method that we use, this cluster isn't going to cost you an arm and a leg either. It's very efficient at processing these events as they happen. So you can use fairly minimal compute infrastructure to actually read the stream, and process it, but still get incredibly fresh features that you can use for your models. All right, I'm going to pause here and answer a few more of the questions I saw in the chat. First was, what kind of storage does Tecton use for the offline feature store? So the data that we actually store, the offline, is stored in S3 and Parquet files. Basically, we say value of this feature was this at this point in time. And when you go look up a feature, we efficiently go in and grab, say if you ask for the value of feature at some point in time, we say, what was the most recent value that was computed for, say, that user at that point in time, and look it up. I'll show you what that API looks like in a second too. Second question was, how does Tecton handle system failures? Say a node fails and it comes back later. Do we guarantee feature accuracy and exactly one style processing? Yeah, it's a good question. In particular, in streaming, either the stream fails or a node goes down, sort of like you saw before. And we handle processing the stream fairly intelligently, moving the watermark around. It's also fairly configurable what the exact behavior you expect should be, so really flexible in that. But essentially, if our node goes down and then comes back, we'll process whatever data is new from the last data that we processed on a stream. And then we can also fill in gaps in our data from historical data store, the historical offline data store, to make sure that we have a full picture of the data. So a few different tools there to handle and be fault tolerant. All right, now let's move into the last thing I wanted to talk about, which was these on-demand features. So in the case of the on-demand feature, we have these transaction events that are happening, and we're passing that data to Kinesis and getting these aggregates. But as we saw, the latency can be, order of a second for this type of aggregate. And if you're processing transactions, if you're, say, a credit card company and you need to handle a transaction, you can't wait a second to learn about the current transaction. And so what the solution is to pass information about the current transaction directly into Tecton. And then we can transform that in, order of milliseconds to features while we're looking up all these other features to end up computing whatever you need from the current transaction. So the feature that I'm going to build here is the last transaction larger than the user's average transaction? One of the cool things this is going to do is it's going to use information about the current transaction. So we're going to pass in the amount of the current transaction. And it's also going to look up information about historical transactions that a user has made. In this case, the features that we defined that had metrics about the user's historical transactions. And that's all going to come together to build this, this feature. So I want to show you what this looks like in Tecton, because these on-demand features are a little bit different and pretty interesting. So I pulled up the implementation here of the on-demand feature that is the transaction amount higher than the average transaction? And probably the first thing you'll notice is this feature is actually implemented directly in Python. So for these on-demand features, you're actually going to write basically like some pandas code that processes this data at request time and turns it into a feature. So in this case, this function has two arguments. One is the request data. So this is information that came in from the request. The schema of this is defined up here. And so what it is, basically the contents of it are a single column that's the amount of the transaction. So inside of here, we should expect an amount or a column, and we can see that we use it here, that basically contains the amount of the current transaction. The other data we get is metrics about historical transactions. And this is actually one of the features that we defined. So the other input to this function is the feature that we had. You can remember we defined it as this user account metrics here. So we have user transaction amount metrics, and that's the second argument to this function. And then this function, really simply what it's going to do, first off, it's going to look up the average size of a transaction in the last, actually in this case, it looks like 72 hours. And then it's going to say, is this amount, I was messing around and it says 24 hours. And then is this amount higher than, like, is the amount of the current transaction greater than the amount of the historical average? And this first line is just filling in nans. So if the user has made no transactions in the last 24 hours, the value of this feature is going to be none. We replace that with 0. So what this all comes together is what gets returned is simply a 1-0 flag. Is the current transaction higher than the average transaction a user has made in the last 24 hours? Now that this is defined, we can go use it. So one more time, we can head back to our notebook and again, I'm going to get this feature, transaction amount is higher than average. And again, we'll use this API call we have called get feature vector, which is going to be used to test grabbing this feature online. So in this case, we need to include two things to retrieve this feature. One is the user ID. So who do we want to look this up for? And we'll look it up for that test customer that we just sent a whole bunch of events for. And then the other piece is some information from the request data. And here we're just going to say the amount of the current transaction is 5,000 and whatever. So obviously you can pass more complex data than just the amount of the transaction here. But in this case, we have this one feature. So when I run this, it basically says, is this $5,000 transaction higher than the average transaction that a user has made in the last 24 hours? And what comes back? 0. No, it's not. Let's bump that up to 10,000. In this case, it is higher than the average that this user has made. And so what this looks like altogether is basically, now we have a couple of features. We have metrics about historical transactions. We have real-time counts of how many transactions users have made. We have the ability to do this on-demand feature of whether or not some transaction amount is higher than the average transaction amount for a user. How this all comes together, we're going to do this in the form of, we have all these cool features, want to use them all together. How do we generate training data is essentially what I want to do next. Because we've shown you like how you query these all online. We have this online API that we can use to query all of these features in real time. If I want to generate training data with all this together, what do I do? And we're going to use some convenient Tecton APIs to do this. And I guess before I really dive into it, the first thing to think about when you think about what this training data is going to look like is essentially what we're going to do is attempt to have a training data set where we have a label, which is a transaction fraudulent? And we have all of our features that we just defined joined onto that. And so you can imagine sort of like the basis of all of this is going to be just historical transactions that a user has made. So here what I have is a whole bunch of these events that I have previously sent to Tecton. You can see I didn't have the random amount at first, but here are events historically for this test user. So these are ones that I sent to the last few days. It says this user made a transaction of this amount at this point in time, and it's labeled as not fraudulent. So what our goal is to basically all of those features we just defined, join them on here and say, what were the values of those features at the time of these historical transactions? And that'll be what our training data is. And Tecton has a really convenient API to do this. if I have a data frame of events that look like this, I've got them stored in this training events data frame, then I can use this method that Tecton has called get historical features. We've grouped all of those features together in this thing called a feature service in Tecton. You don't need to know much about it other than within this feature service, it basically just says, I want to retrieve all of those features that I just defined. So this method from Tecton returns this thing called training data. And if we display it, we've only got a few rows. It looks like I didn't run it on this, but let me run it again. This will take a few minutes, so I'll run it afterwards while we're asking questions. But basically it says, for this user at this time, when they made a transaction of this amount, here's all of the data, all of the values of the features about it. So here were two back-to-back transactions I made, basically. You can see the transaction count, the real-time transaction count incremented from 1 to 2. The long window transaction counts didn't increment, and that's because there's a delay in processing. So since we have a 30-minute slide window and 30 minutes hasn't passed since when the transactions happened here, we would not expect these aggregations to be updated. Same with those metrics. Those metrics had a 10-minute slide window, and since 10 minutes haven't passed, these don't get accounted for in the metrics here. And that's because when we looked these features up online at that point in time, we wouldn't have seen any aggregations or any data for these aggregations as of those points in time. Now let's run this with this increased set of data. I'm going to, for these 11 events, show this, and we'll get a more rich view of how this data evolves over time, what these metrics look like over time, and how Tecton can sort of run all of those different transformations, those real-time aggregations, those on-demand features, how I can run those against historical data to generate all of my training data here. And as I said, I expect this to take a handful of minutes. We're working with Spark and S3 and a relatively small cluster, so this will take just a minute, but give me an opportunity here to pause while this is running and answer some questions in the chat. So now's a great time if you've been holding any questions to shoot some things in the chat, and they can be about anything. Tecton, sort of these individual features that we saw here, or whatever you're curious about. So feel free to ask away. First one I see is, can Tecton be deployed as a Kubernetes construct? It's a good question. So Tecton is a managed service. What I mean by that is it's only available as a software that's sort of like a SaaS software offering that Tecton manages. So it can't be managed on-prem or deployed into an arbitrary Kubernetes cluster. We actually orchestrate a lot of sort of cloud native pieces. So you can imagine in AWS where orchestrating a Spark provider like Databricks here or something like EMR, or orchestrating DynamoDB within your account and S3 within your account and things like that. So yeah. Another question, does Tecton also deal with the identification of fraud in insurance? And if yes, what in your experience data features are most important for fraud detection? The most common thing I've worked with, so we've done a lot of work with insurance companies and with fraud in insurance companies. Unfortunately, I haven't done a ton of work on that. So I'm probably not a great resource for what data and features are most important. I do know that I've worked with people doing a lot of like the registration workflow around fraud. So when you're applying for a claim and things like that, and trying to understand whether or not that's fraudulent. And so a lot of what happens is sort of like the information that a user inputs when they're applying for a claim or something like that, alongside historical information about them and their policy and things like that, can all get fused together to this fraud detection. But the actual nuances of insurance fraud, I'm by no means an expert in, so I don't want to speculate blindly. But it's certainly, because Tecton can handle sort of like the live information someone input for a claim, historical information about that user, their historical claims, their historical use of or their policies, et cetera. And if you set it all together, I think it's a really well-positioned tool. And that's why a lot of insurance companies have turned to Tecton for that kind of thing. Yes, the monitoring of features that I promised I'd show you and then I didn't, in terms of understanding the timing of jobs and things like that. That's a great question. I'm going to open the continuous transaction count feature that I showed you in the UI. And I just want to show you some of the key pieces here that I think of for monitoring. So one is the freshness of data. It looks like here we're seeing freshness of something like 34 seconds, 17 seconds. Every time we refresh this, it says like, what's the most recent data we've processed. If this number gets too high, there's a lot of tinkering you can do on the streaming infrastructure, like I said, that can help you try to drive it down. But if you can't get it to some place that you're actually comfortable with it, I guess let's also like show you the difference between that continuous and the non-continuous one. So here it looks like we actually have like 2-hour unfresh data for whatever reason. I think this is using spot instances, so we may be unfresh here because of that. A lot of visibility to see just like how fresh data is, and that can give you a sense of how new things are. If you want more details, you can always click through to the actual job itself and understand exactly what's going on, how that cluster's running. See, this one is actually running. We can get the Spark UI, things like that. Also, just some general monitoring about the health, like how quickly are we streaming, like processing events. You can see how quickly they're coming in, what the serving delay is here, the write rate online, et cetera. So just a lot of metrics passed through here that you can use to monitor the health of this and get a sense of, is this something that we're comfortable with how fresh this is? Do we need to change this to be something we process in more real time, et cetera? Next question is there a fundamental difference between Tecton's feature store solutions, for example, Google selection or solution Vertex? That's a great question. At Tecton, we kind of think of ourselves as slightly more than a feature store, more of kind of like a feature platform. And the main reason is a lot of tools out there that are offering feature stores right now are really quite focused on the literal store part. So what that means is they sort of leave you on your own to figure out how you're going to compute features and store them in the feature store. And then they basically just maintain these storage layers and provide some APIs for querying. I think that really leaves out the story of how hard it is to actually build these pipelines that are writing features to these feature stores. In particular, things like stream processing, which I've worked with just a ton of companies in my time at Tecton, where writing efficient code to process streams and doing it in a way that provides parity between what's happening online and offline, really, really challenging for them. And because Tecton really is focused on both that storage and serving net layer, but also the transformation layer, we can provide a lot of useful tools to make it simpler to build these pipelines to compute these complex features. And that fundamentally is a lot different from the people who are just building feature stores. I think it provides a more robust solution and maybe a little bit better of a layer of how data scientists can build transformations and how that actually ends up resulting in these features being available to real-time models. Jason asked if there's a way to monitor descriptive stats for features to examine drift. And that's actually not available in the product right now, but it is something we're working on. There's some preview docs that we can share about it, but essentially we're building an integration with a tool called Great Expectations, if you're familiar with it. And what that will do is allow you to profile both your training data as well as the data being served to your models at some cadence. And be alerted if there are any quality issues. So it can be as simple as things like too many null values, or as complex as distribution changes between training and serving that might help you identify drift quickly and be alerted about it proactively. So that's a project we're working on with a target in the fourth quarter of this year to be integrated into the product. Yeah. We can check in now on this. It looks like still running. Our cluster is way under provisioned for this. Looks like someone else is running a big beefy job somewhere else. This might not finish in the next 4 minutes. Not a big deal. I'm going to stick around for the next 4 minutes. I have any other questions come in, but for anybody who attended and needs to drop in the next 4 minutes or drops before I finish answering questions, thank you all so much for coming. I hope you learned something. The recording will be available and sent out to attendees. So if you want to share it or rewatch it or have any curiosities, you're more than welcome to see it there. Feel free to ask us any questions in our Slack. We have a Feast Tecton community Slack. That's an awesome spot to go ask us questions. I'm there, so if you have anything, feel free to tag me there. Again, my name is David Hershey, or anybody on the team, and we'll help you out. So anything you're curious about after this, please feel free to answer or ask any questions there or follow up with us. I'm going to keep asking questions, but again, thank you all for attending. I hope you enjoyed it. Adrian said about features management. Tecton has support to manage different versions of a feature. Yes, we do. So as a natural thing that happens is you do an update to the logic of a feature or something changes. It's a sticky thing always because you probably have models that are dependent on the feature you already trained or built. So you need to be somewhat delicate with how you handle those changes. And we have support to basically run 2 pipelines at the same time for 2 different versions of a feature. And a lot of the metadata that helps you track what models are consuming what features allows you to sort of systematically go through, update your models, test your new models, and hopefully slowly deprecate the old version. But we have specific tooling to help make it easy to organize multiple versions of features. Kristen said, do you offer possibilities to calculate more advanced features like exponentially decayed by time? That's actually a great use case for on-demand features that I've seen. You can sort of get a list of historical feature values and then roll your own exponential decay or things like that. I've seen some users do that. We have handful support within this specialized aggregation tool for something like 14 different aggregations out of the box, but there's a lot you can do by then applying those on-demand features to do some cool things on top of that. Tuna asked about offline sources like Hive tables, and you can just sort of register those with Tecton. Very, very simple. Hive, S3, Snowflake, Redshift, all of that. The main difference you'll notice when you build features on top of that is essentially they operate on a batch schedule. So you are specifying to run a job every day or every hour or whatever it may be that computes the new value of those features and runs it. But otherwise, almost everything looks very, very similar. Support for custom developed features, very flexible in the language. So since you use Spark primarily to define these features, there's a lot of flexibility in terms of how you actually can develop and define features. They can be way more complex than just those specific aggregations that we have. This was really just focused on those aggregations today. And then if you, it's time and I actually have to run to another meeting. I highly recommend taking some of these questions I didn't get to, these last few, and asking them in the community Slack. It's a great resource. I'm happy to follow up. I do have to run to my next thing, unfortunately, but yeah, again, thank you all for coming. It was great, and the questions were all really great too. So yeah, hope you learned something. I hope you all have a great rest of your day, and I hope to see you all in the community Slack sometime soon. Take care, everybody.